So classical probability theory tells us that we expect to see certain kinds of correlations between the outcomes of measurements and the preparations we've done. Quantum theory tells us we expect to see other kinds of correlations. And so there's an effort to understand something about the landscape of possible ways you could have those kinds of correlations. So anyways, this is just a caricature that I made for a talk once about a possible landscape. So it's really, the details here are not important. But the point is that we want to try to come up with some principles that pick out quantum theory from among all these other possible ways that the world could have been. All right, so the kinds of questions we want to answer, we mentioned this on the first day. Why are preparation procedures represented by density operators? Why are measurement procedures represented by POVMs? Why the Born rule for calculating probabilities of outcomes of measurements? And in particular, why is it a rule that's linear in the quantum state as opposed to anything else? Why is composition of systems represented by tensor product? There's lots of other products. And then questions like, why Hilbert space over the complex field? Why not the real field, for example? Why Hilbert space at all? There's lots of other possible mathematical objects that could have described the preparations and the measurements in your theory, all of which would have given you possibilities for other kinds of statistics. So this is our target. We want to answer these kinds of questions. So what I'm going to do is I'm going to take you through a formalism that was developed by Lucian Hardy back in 2001. And the idea here is now to come up with a framework for even describing general theories. Like one of the challenges we have is if we're doing quantum theory, we've got Hilbert space as our background framework. Classical probabilistic theories, it's something else. You really need a framework that's powerful enough to describe all of these possibilities and others besides them, quantum, classical, and everything else. So this is an attempt to develop such a framework so that we can even describe these other alternatives. So again, it's going to be an operational approach. So the task is going to be to represent mathematically preparation procedures, measurement procedures, and have an algorithm for calculating the probabilities of outcomes of those measurements. So here's the idea. If we consider all the possible measurements that you might do in this possible world you're describing, so let's say measurement 1 has 2 outcomes labeled 1 and 2. Measurement 2 has 3 outcomes labeled 1, 2, and 3. And now just write down the vector that gives you the probability distribution over the outcomes of measurement 1 and the distribution of the outcomes of measurement 2, and so on, for every measurement. So it's a really long vector. But it's certainly sufficient to make predictions about the outcomes of any experiment. Our task here is we want something to represent the preparation which will give us a catalog of expectations. It'll tell us what to expect for any given measurement we might do. So this will certainly do it, because if I do one of those measurements, all I need to do is represent it by a vector that's 0 everywhere except at the kth outcome for the measurement I'm interested in. And then I take the inner product of this with this S vector, and I pick out exactly the probability I'm interested in. So that's a simple algorithm that will allow me to predict the outcomes of all measurements using this representative of the preparation. But of course, it's extremely inefficient as a representation. So let's do better. So I introduced the notion of a fiducial measurement. A fiducial measurement is going to be a pass-fail measurement. So it's going to be a measurement that has only 2 outcomes. And I'm just going to label one of the outcomes pass, one of the outcomes fail. And a set of fiducial measurements has the property that if you know the statistics for those k fiducial measurements, you then know the statistics for any other measurement. So let me give you an example of that in quantum theory. So suppose you want to do tomography on a state. So that's jargon for you have a preparation procedure that puts out a system prepared in that state. And you can do it as many times as you like. And so you can calculate statistics. You can do measurement 1 a large number of times on that preparation, find the statistics of the outcomes of measurement 1, then move on to measurement 2, and so on. And so you can ask, if this system is just a qubit, a 2-dimensional system, what's a fiducial set of measurements? There's an infinite number of measurements I can do on the qubit. Every direction in the Bloch sphere corresponds to a different measurement. But I don't have to do an infinite number of measurements to characterize what state is associated with that preparation. it suffices to do 3 measurements. So I could do a z-spin measurement. Let's say the vertical axis is the z-spin axis. So if I do the z-spin measurement and I calculate a lot of statistics and I get an expectation value for z-spin, or equivalently a probability for z being up, that puts me somewhere along this line. So this green plane, for example, could be the probability of z up that I found. So I know that the state that is coming out of this device is somewhere in the intersection of this green plane and the block ball. So it's somewhere in this disk. And then I come along and I do a measurement of x spin, and that tells me now that I'm somewhere along this line. And then finally, I do a measurement of y spin, which tells me I'm in this blue plane here. And so I've located myself down to a point, and I'm done. I know exactly what the density operator is for that preparation. So out of the infinite measurements in quantum theory, 3 are enough to do tomography. So that's what I mean by a set of fiducial measurements. So the claim is that in any theory you give me, there will always be some set of fiducial measurements. At the worst, it's all of them. It might, you could imagine a theory where there's no shorthand. You have to do all measurements to be able to predict all measurements. No subset of measurements is adequate for predicting the rest. But in general, theories have some structure, and that's not the case. OK, so now if you've got a fiducial set of measurements, it's sufficient to specify the preparation procedure. It's sufficient to provide a vector which just gives you the probability of passing every one of your k fiducial measurements. The probability of failing, of course, is just 1 minus the probability of passing, so there's no extra information there. And this is, of course, a much shorter vector than the one we had before. Now, so I'm going to call that the operational state. So it's a characterization of the preparation procedure. And by assumption, the probability for the outcome k of any other measurement m, not necessarily one of these fiducial ones, but any measurement m, is just going to be given by some function of this vector s. That's what I meant by the fiducial measurements. Their statistics were sufficient for calculating the statistics of anything else, which means that there is some function that will give me those other statistics given these ones. So what we want to know is, what can we say about f? And what I want to try to convince you of is some very mild, weak assumptions about how any theory should work can already highly constrain the nature of this rule for calculating probabilities. So is it clear what the game is here? Good. All right, so let's start constraining f. So I'm going to use a fact about preparation procedures, which is that it's always possible to, if I have 2 preparation procedures, p and p prime, to make a new procedure p double prime, which is just a mixture of p and p prime with probabilities w and 1 minus w, for example. And if I do that, then for any measurement over here, the statistics I'm going to predict for this measurement on p double prime, that's this thing here, is just going to be the weighted sum of the statistics for p and p prime. And the reason is just classical probability theory. This is the probability of getting outcome k given that I prepared p times the probability that I really did prepare p plus the probability of getting outcome k given that I prepared p prime times the probability I prepared p prime. That's the overall probability of getting k for this procedure. So that's got to be right. As long as there's nothing in my the world I'm imagining that prevents me from choosing what preparation to do based on the flip of a coin, then this is fine. And so this is a very mild assumption at this stage. And what it means is that this f function that I defined, I'm going to drop the subscript mk for now. Well, that function evaluated on the vector for p double prime is just the same convex combination of the function evaluated on p and p prime. But this should also be true for the fiducial measurements that we defined, right? So if I go back, although it's not clear what this function should look like for a general measurement, if it's one of these fiducial measurements, then again, it's that same scheme where all I need is to take the dot product with the vector that's 1 in the appropriate spot and 0 everywhere else. So for the fiducial measurements, this is just a dot product with a vector, and it's linear in S. And in particular, if I take the dot product with something that picks out just the first component, then I find that this whole equation is true for the first components of these S vectors. And I can also find that it's true for the second components, and so on. So if it's true for all the components, that means it's true for the vectors themselves. OK? So I know because of the fiducial measurements that this is also true. And it follows, by the way, that the set of vectors which represent the preparation procedures are closed under convex combination. You give me any two vectors, SP and SP prime. Then there's another vector which is given by the convex sum of those two guys with any weight. So the set of preparation procedures that I can do under this assumption that I can always flip coins and choose what I'm doing has to form a convex set. So that's the first non-trivial thing we've derived about a general operational theory. Maybe it wasn't totally evident to begin with, but I should be able to represent the set of all preparations by vectors in a real vector space that form a convex set. OK, back to the nature of F. If I combine this equation with this equation, it tells me that F evaluated on a convex sum of guys is just the convex sum of F evaluated on each one. And so this is what I've been calling convex linearity. So now I've shown you that F must be a convex linear function. Now, the next step is to prove that convex linearity actually implies linearity. So far, all I've got is this fact, that for wi's that are between 0 and 1, and that sum to 1, this holds true. But I want to prove that for any linear combination, so now the alpha i's can be any set of real numbers. If S is a linear combination of the SI, then F of S is the same linear combination of F of SI. All right. Well, first of all, as I said before, the fiducial measurements are clearly represented by linear functions because R dot S is linear in S. So for the case of the fiducial measurements, F is a linear function. And the question is, how do I prove it for any measurement, not just the fiducial ones? All right, here's the proof. So I'm given this fact. And now I'm going to do some algebraic manipulations. Take all the alpha i's that are negative. So sort the I index into a set, which I'll call capital I minus, and a set capital I plus, which tells me whether the alpha I is a positive or a negative number. And then I move all the ones that are negative numbers to the left-hand side of this equation, so they become positive. So I can just write this as the absolute values of the alphas. Next, we prove this equation. So to do this, I just have to think about these fiducial measurements. Let me just go back here. Let's see, what's the best way to do this? If I had not just these probabilities here, but also the probability of fail for the first measurement and the probability of fail for the second measurement, then I could have picked out those probabilities by just taking the inner product again with vectors like this, 1 and zeros everywhere, 1 in the second slot, zeros everywhere. And if I ask what's the probability of passing or failing that first measurement, it would be obtained by a dot product with something that would be like 1, 1, and zeros everywhere. And so if I apply the dot product to this equation for such a vector, any S will just give me a probability 1. So it doesn't matter which preparation I'm talking about. If I ask about the trivial fiducial measurement, which sort of always returns the pass outcome, then the probability of that is always 1, no matter what the preparation is. So I can always take a dot product of S with something corresponding to a trivial fiducial measurement, and I get a 1 here, and I get a 1 for all the SIs. And so I just get this equation. Now, I went through that a bit quickly. Is that clear why that should be true?
Why do you call that a coarse grain?
Why do I call that a coarse graining? So I realize now that I've made my life a bit difficult because I left out all the probabilities of the fail outcomes because they weren't really giving me any new information. OK, let me try explaining it a different way. If I had if I had made one of these measurements a trivial measurement, right? Something that always gives the yes outcome, right? Like, is the system there? Every preparation procedure gives probability 1 of outcome yes. Then no matter what p was, the first component of this SP vector would always be 1 for all the preparations. And so then if I just looked at the first component of this equation, that's what I'm assuming, right? Then it would be, the first component would be 1 for this guy and 1 for all the SIs. And so using that, I can conclude that sum over I alpha I is just 1. That's the idea. OK? So I haven't assumed anything sort of physically deep here. It's just a fact about the normalization of these linear coefficients.
How
Yes?
do you know it's linear in the fiducial measurements?
Because by definition, I can always pull out the probability of a pass for any fiducial measurement by taking the dot product with this kind of vector. And any function of this form is clearly linear in the S's. Because if I take a linear combination of these guys, I can just pull those out. So that's why it's linear for the fiducial measurements. OK. Once you believe this, the rest is, again, just algebraic manipulation. So what we do is the same sort of trick. We move all the negative alpha i's to the left of this equation. And that gives me this equation. And I'm just going to define whatever this scalar is. It's a positive number. I'll define that as script n. All right. Now, start with this equation here. Divide through by this n I've just defined. And now you'll see why we're doing all this. If I sum up all the coefficients on the left-hand side of this equation, I'm going to get 1. Because if I look at the definition of n, it's 1 plus the sum of all these guys. So if I sum all these guys up, I'll get 1. They're all positive as well. So I know that I can think of this as a probability distribution. It's a set of positive numbers that sum to 1. So now the left-hand side of my equation is a convex combination of these S vectors. That's good, because I know I have convex linearity. And so I'm going to be able to apply, if I apply f to this equation, I'm going to be able to use the convex linearity property, because I've reduced it to a convex sum. And similarly, the right-hand side is also a convex sum of the SIs, because the sum of the alpha i's is n. So if I divide by n, I get something that sums to 1, and they're all positive. So the rest of the proof is straightforward. I apply f to both sides of this equation. I use convex linearity. I get this form. And then I just move this stuff back to the right-hand side of the equation. And I multiply through by n. And I get precisely what I was looking to derive here. Yes?
So in general, convex linearity per se does not imply linearity. You do need to assume that f is linear on some fiducial set.
That's right. But to some extent, it's not so much an assumption as we've defined the operational state to be that thing which returns the probabilities for outcomes of fiducial measurements via a linear function. That's what its components are. And so once you've defined the operational state that way, then this proof follows. And so sort of surprisingly, once you've defined things in that way, you find that, oh, all measurements are now represented by linear functions over the set. Good. OK, so we know now that f is a linear function, not just any old function. And every linear function can be represented over a vector s, can always be represented as an inner product of s with some other vector. That's sometimes called the Ritz representation theorem. And I mean, that's not hard to prove. It's just, it's a linear function in all the components of s. So whatever the coefficients of those linear components are, well, collect them together in a vector. That's R. So there's nothing profound about this result. So that's quite nice. It says that out of all the possibilities for what f might have been, it has a very constrained form. It's linear. And it all follows from this assumption of convex linearity, which was a very weak assumption on our operational theory. All right, let's now see what we can say about a general operational theory. Well, we know that any preparation now can be mathematically represented by a set of vectors in a real vector space. This is just sort of the way we've defined things. But furthermore, the set of such vectors has to form a convex set. So it has some structure. And these guys over here, the measurements, can always be represented by linear functions, which means that they can always be represented by other vectors in this real vector space, which I use to take the inner product with S to return those probabilities. So for every measurement and every outcome K of that measurement, there's some vector that will allow me to calculate those probabilities. And these things are sometimes called the operational effects. So a particular outcome of a particular measurement, there's a sort of jargon that people call these things effects. And you can also figure out what the geometrical structure formed by these guys are. They're not arbitrary. And it turns out to be the interval of a positive cone. Yes?
Just you said the vectors S are real vectors. Are you saying the vectors R are real and positive? Or this is an interval of positive cone?
The vectors S, they happen to be embedded in a real vector space. But yes, you can certainly represent it by vectors, all of whose components are positive. I can always, if I want, sort of move everything, I can do a rotation in my real vector space and start representing both of these guys by vectors that aren't strictly positive components, as long as these inner products are still positive. That's what I really need. I want to make sure that all the probabilities come out positive. And the way I've defined things, they come out positive because all the components of this guy are positive. But in general, I can let these components go negative as long as this thing stays positive. The one thing I can say for certain about how to represent these preparations is that they have to form a convex set. And the difference between different theories is actually going to come in the shape of those convex sets. And that's what I'm going to talk about next. So I'm not going to actually say a lot about why the operational effects form a cone in general. I think that would sort of get us into details that aren't that interesting. So as I said, it's these sets S and R that ultimately tell you where you are in the landscape of possible theories. So let's look at some examples. Take just classical theory, understood as an operational framework for making predictions about the probabilities of outcomes of experiments. In that case, you can think of these vectors S as probability distributions over some sample space, some classical sample space. And the set, the convex set, is just a simplex. So here's an example. Suppose you have a sample space consisting of just two elements, which I'll denote 1 and 2. So these might be two physical states, like maybe you have a coin, heads and tails. So the possible preparations you might make of that system are just the possible probability distributions over that two-element space. And I can draw it this way. So in a two-dimensional real vector space, the case where it's definitely going to be state 2 is 0. Probability of 1 is 0. Probability of 2 is 1. That's this point here. The opposite case where it's definitely 1 is this point here. In between, I have probability half-half. And I have every possible bias of the coin in between. OK, so this is a line is a very simple example of a convex set. And it's embedded in this two-dimensional real vector space. If you ask, well, what about the measurements? The answer is an outcome of a measurement can be any vector of conditional probabilities. And the set of these guys forms a unit hypercube. Here's how that works. So again, let's imagine just an outcome of my measurement, which I'll call the pass outcome. And the vector R specifies the probability of passing this test if the physical state is 1, and the probability of passing if the physical state is 2. And so, for example, I could imagine a measurement that was at this point, which said that it is never passed if the state is 1, and it's always passed if the state is 2. So it's probability, conditional probability 0 and 1. Or I can imagine a measurement over here, which is never passed if the state is 2, but always passed if the state is 1. So it's probability 0 and probability 1. Or there's a trivial measurement that's always passed regardless of what the state is, and another one that's never passed regardless of what the state is. Yes?
So when you say the unit hypercube, are you thinking of the hypercube as in a surface plus everything that's inside?
Yes, that's right.
But for the simplex, you're talking about just the surface?
Yeah, here, so I guess I might have done better by coloring this all in blue. So here the set is just what's in the red line. Here it's the whole interior of the square. That's right. And the reason this is, well, let me show you how you calculate the overall probability of passing. So if your preparation procedure is represented by a point in this space, and your measurement is represented by a point in this space, then to find out the overall probability of passing that test for that preparation, I just take the inner product of R and S. And that just gives me the probability of passing, given that the physical state of the coin was I, times the probability that the physical state of the coin was I, summed over I, which of course is the overall probability of passing. This is incidentally called a cone because if I sort of imagine going out this way, it has the shape of a cone. And so it's really the intersection sort of a forward cone and a backward cone, starting from these 2 points here. Let's look at a slightly more complicated example where we have now 3 physical states. So this is like a dice that has 3 possible outcomes. Well, then the set of preparations is the convex set, which is the triangle, which is the next more complicated simplex after a line. And so there's preparations where it's definitely prepared in state 1, definitely prepared in state 2 or 3, and every probabilistic combination of those guys. And the measurements just are the vectors of conditional probabilities, probability of passing given that it's state 1, 2, or 3. And here are all the possibilities. These are all the extremal points for what those conditional probabilities might be. And everything else is convex combinations of those guys. And of course, the formula for calculating the overall probability is exactly the same. So again, this looks like a cone if I sort of imagine the ray coming out of the origin through this to the middle of this octant. So all I've done here is I've given you this kind of geometric characterization of classical probability theory in terms of the shape of the convex set of preparation procedures and the shape of the positive cone of operational effects. So let's compare this now to what we have for quantum theory. So how am I going to represent quantum theory in a real vector space? We've already seen this. It turns out that the Hermitian operators on a Hilbert space of dimension d do form a real vector space of dimension d squared. So I just think of all the operators as vectors in a vector space. They're closed under linear combination and scalar multiplication, so they form a vector space. And it's a vector space over the reals. So I can just think of my density operators as vectors in a vector space. And I know that the density operators are all unit trace positive operators. So rho is positive, trace of rho is 1. And that is going to define a subset of all the vectors in this vector space of Hermitian operators. Yes?
So Hermitian operators form a real vector space. And a moment ago you said they form a vector space over the reals. That means
the same thing.
Okay. So my perhaps erroneous understanding of what a vector space over something is what it's over consists of the coefficients of
That's right.
the elements of the vector space. So are you saying that Hermitian operators can have just real coefficients?
What I'm saying is that if I take 2 Hermitian operators A and B, and I ask, what are the constraints on alpha and beta such that the linear combination here is also a Hermitian operator? Alpha and beta have to be real. If I threw in a complex alpha or beta here, then what came out wouldn't necessarily be Hermitian. Because when I take the dagger of this thing, I'm going to take the complex conjugate of these coefficients. And similarly with scalar multiplication, I have to constrain myself to the reals to make sure that I stay within the set of Hermitian operators. So the question we have before us is we need to figure out the shape of the convex set of Hermitian operators which happen to also be positive unit trace operators. So can anyone tell me what the shape of that convex set is? That's actually a really hard question. Let me make it easier for you. Say I had a two-dimensional system. What's the shape of the convex set of density operators?
Ball.
It's a ball. Exactly. This is what you saw in the first tutorial. So you thought you were just seeing another representation of quantum mechanics for a two-dimensional operator. But in fact, you were seeing a real vector space representation. And you were looking at the convex set of density operators. So for a single qubit, it's two-dimensional. The space of Hermitian operators on a two-dimensional complex Hilbert space is a four-dimensional real vector space. And it's spanned by the Pauli operators. So just as any vector space of dimension d squared, I can find an orthonormal set of vectors that span that space. This is an orthogonal set of vectors for the vector space of Hermitian operators. And it means that I can write any other operator as a linear combination of these guys with real coefficients. So in particular, I can write any density operator as a linear combination of these guys with real coefficients. And it turns out that if you ask, well, what is the constraint on these coefficients such that rho is positive and unit trace, the answer is that S naught here has to be 1. And these other three components, which I've labeled S prime, S here in this notation is going to be all four components. S prime is just going to be a real vector whose length is less than 1. And so that's these two constraints. Although normally I would have to draw this in a four-dimensional space, because that's what's embedded in. Because S naught's always 1, I can just draw what the space of the S primes is, and it's a sphere. It's all the points that are within radius 1. Question? Yeah?
So I still am not entirely certain what precisely is the role of the Hermitian operators. So you started out by mentioning the Hermitian operators. Then it seems that you said that any preparation procedure can be represented in terms of any unit trace positive operator, and then you introduced constraints on those positive operators. But so we have a bunch of positive operators that have certain constraints on them separately or not. We have Hermitian operators. I'm not sure exactly what role the Hermitian operators play.
Okay. So if I was doing a general theory, not quantum theory, but just general theory, then what I've shown you is that I can always describe the preparation procedures by some convex set of vectors, which can be embedded in some real vector space of a certain dimension. And now my task is, okay, well, how can we represent quantum mechanics in this way? And so the embedding space, kind of the larger vector space in which I'm going to describe the preparation procedures, that's going to be the set of all Hermitian operators, which forms a real vector space of dimension d squared. So call that the embedding space. And then when you look at the subset of Hermitian operators that actually describe preparation procedures, those are the positive unit trace ones, they form a convex set that lives in that vector space. And the shape of that convex set is the ball. Does that clarify things? Yeah? Okay, so again, remember that ideally I would draw this in a four-dimensional space, but that's hard to do in this three-dimensional world of ours. So I'm just showing you the three-dimensional cross-section when S naught's equal to 1. Okay, the R vectors that are going to represent the operational effects, well, we know that a measurement and an outcome of measurement are always associated with a positive operator that appears in some resolution of identity. So I'm talking here about elements of a binomial. So an element of a POVM, I'll just call it E, it has to be positive, because it's a positive operator value vector. But also, identity minus that element has to be positive, because identity minus that element is really the sum of all the other elements that appear in POVM, and they're all positive. And the sum of positive operators is a positive operator. So the most general thing I can say about an operator that appears in some POVM is that it's positive, and this is positive. And people sometimes also describe that as the operator being less than identity. So if I wrote the positivity condition as just this, then I could also write it this way. It's just a shorthand notation for that fact, that identity minus E is a positive operator. So that's why I call it less than identity. Okay, so what does that look like when I embed it in the vector space of Hermitian operators? Well, we never, neither in tutorial nor lectures, looked at the geometric picture of POVMs. And it's not that hard to do, but I think it would take us too far afield, so we're not really going to cover it. But let me just say that any Hermitian operator, of which a POVM element is an example, can always be written as a linear combination of these basis elements. So I can find some R naught and some 3-vector R prime, which, and I can constrain R naught and I prime such that E is going to be positive, and identity minus E is going to be positive. And when I do that, I find that R naught has to be between 0 and 1, and this R prime vector has to have a length that's both less than or equal to R naught and less than or equal to 1 minus R naught. Now the problem is that if I really wanted to draw these guys out, because R naught is not fixed anymore, it's living in a 4-dimensional space. So what I'm going to do instead is say, just suppose that one of these components is 0. Like say the sigma y component here is just always 0. If I'd done that over here, if I said, let's consider the cases where this S prime vector is 0 for the sigma y component, then I would have had just this, disk here. Okay, so that disk gets reproduced here. And the point is that the operators that can appear in a measurement are not just the states, the density operators, but also things that are subnormalized and supernormalized relative to the density operator. So by that I mean I could take, for example, the projector onto some pure state. That's a projector. It's a positive operator as well. It's something that can appear in POVM. But I can also take 1/2 times that guy, and that would be some point down here. Or I can take epsilon times that guy, and that's a point very close to the 0 operator. But I can also take the identity operator. Something that, the trivial POVM has just the identity operator in it. And the identity operator is this point up here. It has R naught equal to 1, and this R prime equal to 0. So here's the R naught axis, and over here we have the R prime X and R prime Y. Anyways, so if you think carefully about how to represent this, it's 2 cones that are intersecting one another on top of each other. Yes?
Oh, sorry, so this S is not a simplex? Right? Or...
Sorry? This is not a simplex, no.
No, the S, I mean...
No, S is a simplex.
Oh.
So it turns out that if you take any 2 points in S and take the convex combination of those guys, well, we saw in the tutorial that convex combinations correspond to a straight line in this space. So any 2 points on the straight line between 2 points in this are also in this sphere. So the sphere is convex. It's not a polytope. And that's what makes it interestingly different from the classical case. The classical ones were all simplices. And this is definitely not a simplex.
So yeah, that was my question. It's not a simplex. But
sorry, it is a convex set, but it's not a simplex. And that is a fact that we've already talked a lot about. So there's a famous theorem by Carathéodory that says, if you ask how many ways are there of decomposing a point in some geometric shape into a convex combination of the extremal points, for a simplex, the answer is there's just one way. Which corresponds in the classical probability theory to the fact that if I give you a probability distribution, there's only one way of decomposing it into the extremal probability distributions. The extremal ones are the ones that have probability 1 for one physical state and 0 for all the others. Whereas in other kinds of convex sets, like this one, we have many ways of decomposing a state into extremal states. So if I have like a point at the center, I can decompose it this way, or if I have a point over here, I can decompose it lots of different ways, infinite different ways, in fact. So that funny thing we saw about the many different pure state ensembles, all of which lead to the same average mixed state, which was a funny feature of quantum theory, is captured by this difference in the convex sets. And that's good, because I'm trying to convince you that the convex set sort of tells you everything you need to know. Well, the convex set, together with the positive cone of measurements, really characterizes that operational theory. Right, and if I want to calculate, so now I can say, in quantum theory, any preparation procedures represent, well, let me point at these diagrams for the two-dimensional case, but really this holds more generally. If I had a larger dimensional space, it would be harder to draw these things because they would live in much higher dimensional vector spaces and they have more complicated shapes. But let me just point at these diagrams. If I have an arbitrary preparation procedure, that's some point in the convex set of quantum states, and some particular measurement and some particular outcome of that measurement is some point in this space. And the general operational theories tell me the probability of getting that outcome should just be r dot s. And in this vector space of Hermitian operators, the inner product is the Hilbert-Schmidt inner product, which we talked about last time. So it's just trace of the Hermitian operator that represents the state and the Hermitian operator that represents the effect. So that's just trace rho e, and that's the Born rule. Okay, so we've confirmed that this general form of the statistical rule is indeed obeyed by quantum mechanics when I think about it as embedded in the vector space. Yes?
So you said earlier, suppose that we think of one of the components of R as always equaling 0, and
Yes.
that enables us to represent our geometric figure in the space that we can see.
Yes.
In general, when we're dealing with quantum theory, we still want to make that assumption that some component.
No. I can certainly describe the positive cone of effects as this set of R vectors, the ones that have these kinds of components. And that's really what I want to say for a two-dimensional Hilbert space. This is the correct set of operational effects. The whole business about setting one of these guys 0 is just me telling you what this little picture means. Just because I thought it would be nice to see a picture rather than just seeing something abstract. It's really not so critical to see the picture, but I find that often having a geometric intuition about what's going on is helpful. And so even though this doesn't capture all of the effects for two-dimensional Hilbert space, it's sort of useful to see it. One thing that I can say, based on these pictures, is that classical probability theory can be embedded in operational quantum theory. So for example, if I told you you can only do preparations that are diagonal in the z-spin basis, well, that would correspond to being able to prepare density operators that were linear combinations of identity and sigma z. And that corresponds to only density operators that lie on this line. They're convex combinations of z-spin up and z-spin down. So we're back to that line, which was the first classical state space I showed you. It's a simplest simplex. So that's the classical state space. And then similarly, if I go over here and I say, well, what are the POVM elements that lie in that two-dimensional subspace of the space of Hermitian operators, it's just the square here. So imagine just taking a slice, to draw the line through here, and that's the whole square. And that's also exactly the effect space we saw in that first classical example all the way back here. That's square. So the classical state spaces can be embedded in the quantum state spaces as a special case. Good. So now I want to do just a bit of. I tried to convince you early on that these abstract mathematical axioms we had for quantum theory, even the ones that the improved ones that don't make reference to physical states of the systems, that we'd really like to replace those with more physical principles. So I'm just going to show you a little bit of how to do that. So imagine this. Suppose you start with the following assumption, that the convex set of preparation procedures is just represented by the positive trace 1 operators on some complex Hilbert space. So I've already given you a huge amount of quantum mechanics, by saying that. And you should rightfully ask, well, why? And why Hilbert space, all that stuff. And I'm not trying to answer those questions here. I'm just saying, let's suppose we start here, and then we might ask, well, is there some other elements of the formalism that are now fixed because of that assumption, that aren't variable any longer? And I'm going to try to convince you that there are. So I'm going to make one other assumption, which, again, I'm going to take this to be not an abstract mathematical assumption, but a rather mild physical assumption, that every logically possible measurement is physically possible. By which I mean, if I describe a measurement, and it has all positive probabilities for its outcomes, so there's no negative probabilities, there's no probabilities going greater than 1, so I could conceive of this measurement being done, then I'm going to imagine that it's possible to find a way of implementing it in the world. And we saw that was true of quantum mechanics. As soon as I characterized intrinsically what would generate positive probabilities for measurement outcomes, we found that there was always a way of implementing those kinds of measurements. So I'm just going to assume that. Okay, so what this means technically is that I'm going to, once I've told you what the set of S are, that's this here, I'm going to allow all sets of R vectors such that every one of them gives me a positive probability for the outcome, K. And it's a positive probability no matter what preparation you did, so for all the vectors in the set S. And furthermore, if I sum over all the different outcomes, well, then that has to give me 1, because this is the probability for getting outcome K, and some outcome has to occur, so these are better summed to 1. And again, that should be true for no matter what the preparation procedure was. So this is just what I mean by all logically possible measurements are physically possible. So now I'm going to embed everything, again, into the real vector space of Hermitian operators, because I know that the convex set, positive trace 1 operators, can be embedded into that space. So I may as well use it. Remember, the inner product between any two Hermitian operators is just given by this Hilbert-Schmidt form. And so in this way, I can associate with every vector S some density operator rho. Again, that's really just what I'm assuming. And the question is, what then are going to be this set of RK vectors, the logically possible ones? So we know that each set of these RKs is going to be some set of Hermitian operators. So even though I'm using this standard EK notation, I have not shown you yet that these things are positive. So right now I'm just saying, look, all this is embedded in a vector space of Hermitian operators. So these guys are going to have to correspond to some set of Hermitian operators. And the question is, what constraints do these conditions place on those Hermitian operators? So remember, RK.S in this representation is just trace EK rho. That's what inner products look like in this space of Hermitian operators. So first of all, let me note that I've already just derived for you the form of the Born rule, right? So through that, that question we had, why is the Born rule linear? The answer is any operational theory that has this simple feature that convex combinations of preparations are also possible preparations. All those theories had to have the probability rule of the form R.S, which made them linear in the states. This assumption tells us already that we have satisfied that assumption. We do have a convex set of preparations. So the probability rule has to look like this, which means that it's going to be trace of something times rho. So we've already got something out of this. You can't change the form of the Born rule to something that's nonlinear in rho and satisfy those mild physical assumptions. But furthermore, if you say, well, let's see what these conditions imply, so just rewrite RK.S as trace EK rho, and it says that trace EK rho has to be greater than 0. Well, for all S, which means for all rho, this here just means all the density operators. And this condition here becomes the fact that some over K trace EK rho has to be 1 for all rho. Now we're getting closer to POVMs. So let's look at those two conditions. Here they are again. In particular, this is true for projectors under pure states. So among all the rows are the projectors under pure states. And if I rewrite this as just the expectation value of EK for psi, I recognize this to be the condition of positivity for EK. So I've derived that the EKs are not just any old Hermitian operators, they have to be positive. And then I do the same thing here. I say, suppose I plug in the pure states for rho. Then I get this condition here. And if you ask what sorts of operators have expectation value for all states in the Hilbert space, the answer is there's only one operator like that, and it's the identity operator. Because anything that's different from identity would have some eigenvalue less than 1, and I could find some vector such that its expectation value was not 1. So this tells me that the sum over k, ek, has to be identity. So now I found that these EKs are not just any old set of information operators, they have to be the POVMs. So the logically possible measurements are just exactly the set of all POVMs. Okay, so what we've derived is, one, the form of the Born rule, and secondly, the fact that the set of operational effects is just the set of all positive operators less than identity. Okay, so this is where I ended last time. You know, these were the new operational axioms for quantum theory. And now what I've tried to convince you of is that if I start with the first axiom and I add another axiom, every logical possible measurement is physically possible, I can actually derive what that second axiom was, that every measurement is associated with a POVM, and the probability of some outcome is given by this Born rule. So this axiom is not logically independent from that one. It actually follows from that one together with this statement about all logical possibilities being physically possible. So that's one way in which the formalism of quantum mechanics is more constrained than the textbook, or these improved textbook axioms might suggest. You can't vary the second axiom while keeping the first axiom fixed. And this is a very similar conclusion to the one that was reached by a famous old result called Gleason's theorem. So you might have heard something called Gleason's theorem. It's a result from the 50s. And Gleason showed something very similar. He actually started by assuming that the measurements in quantum theory were associated with projector valued measures. And then he said, what's the most general function over those guys that could specify a preparation procedure? And he showed that it was the density operators. He did this only, though, for dimension 3 Hilbert space and greater. So he didn't do it for dimension 2, whereas our proof here held even for dimension 2. So he sort of showed that if you assume something like this, then you could get back here. And we've shown that if you assume this, you can get here. So those two axioms about the way you represent preparations and the way you represent measurements are not independently variable. So there's a large literature on this stuff these days, and if we had more time in the course, I could go on and tell you about what sorts of axioms might justify these kinds of postulates. And in particular, the really interesting question is, what sorts of axioms can get you kind of off the ground into Hilbert space over the complex field? What sorts of axioms can get you the tensor product? Now, we're only like 4 minutes out. I think I started a bit late. I had probably 10 more minutes of material on why the complex field. And the question is, should we stop now? Or do you want to hear about why there's a complex field in quantum theory?
If we stop now, do we lose that?
Yeah, you'll never see it again.
I like to.
People okay with that? Well, feel free to leave if I go on too long. All right, so I'm just going to say a few words about what kind of physical principle can get you to Hilbert space over the complex field other than the real field. All right, so what do I even mean by quantum mechanics over the real field? So again, I'm going to think of this as an alternative operational theory, a different way the world might have been. So whereas in quantum theory we know and love, pure preparations are arrays in a complex Hilbert space of dimension d. The repeatable measurements, so these are like the projector values, the projective measurements, they correspond to bases of that d-dimensional Hilbert space, and of course gratings of those. The reversible transformations are unitaries. The mixed state preparations become positive unit trace complex matrices, and the composition rule is just a tensor product. So the new theory is everything's the same, but I replace this complex field with the real field. So the pure preparations are now going to be raised in a d-dimensional vector space over the reals rather than the complex. The repeatable measurements are the bases in such a space. The reversible transformations are not the unitaries, they're the special orthogonal transformations, which are orthogonal transformations that have determinant 1. The orthogonal transformations are the reflections and the rotations. The ones that have determinant 1 are just the rotations. So the reversible transformations in this theory are just the rotations. The mixed preparations are positive unit trace matrices that have real components rather than complex components. And then finally, the composition rule is also tensor product, just like the complex case. So this is the theory I'm talking about. It's conceivable that we could have gone to the lab and found that the statistics of our experiments corresponded to this kind of theory. Why don't we see that? Is there some physical principle that could tell us that such a theory would somehow be strange or not as elegant as a theory that involved a complex field? Well, there's sort of a popular principle that people appeal to in their attempts to derive quantum theory, which has to do with tomography. So we already saw the case of tomography for a single qubit, where it's sufficient to do measurements along 3 spin axes to figure out the state. And the principle that we're going to appeal to involves tomography for pairs of qubits. So I'm just going to look at the qubit case. So I'm going to imagine that you've prepared 2 qubits in some density operator, any old density operator. And the question is, what's a set of measurements I could do? There's an infinite number of measurements I could do on that pair of qubits. What's a set of measurements that's sufficient for reconstructing the density operator of the pair? And it turns out it's sufficient to measure, on one side, choose 1 of 4 measurements, the 4 polys, and on the other qubit, also choose 1 of 4 measurements. So do all 16 possibilities and get statistics for each one of those. And that will be enough to reconstruct it. And to see that, it's enough to notice that the number of parameters for a Hermitian operator on a 4-dimensional Hilbert space, so that Hermitian operator lives in a 16-dimensional space, but it has trace 1. So there would be 16 parameters typically, but the trace 1 condition removes a parameter. So there's 15 parameters. There's a 15-parameter space of 2 qubit density operators. So I know that my measurements have to give me at least 15 different parameters to be able to specify it. I have 4 times 4 measurements, so 16 measurements in all. But the measurement that corresponds to identity, tensor identity, well, that always gives me probability 1. It doesn't give me anything interesting. So I lose 1 parameter there. But the other measurements are still non-trivial. So the measurement is like sigma z tensor identity. Well, that's just the expectation value z on the first qubit. Or if I take sigma x tensor sigma x, that tells me about the correlation of the x spins for the 2 qubits. Those other guys form 15 independent parameters. So it's precisely what we need to reconstruct the density operator. Okay, so what it means is that the mixed state of 2 qubits can be determined from local measurements alone. This set, I didn't require to do a measurement like the Bell basis measurement, which would require me to get the 2 qubits together in my lab and do a joint measurement on them. Even though these 2 qubits are very far apart, I can do these measurements on each one, get the data together, compare the data, and recalculate what the density operator was. So the fact that you can do this with local measurements means that quantum theory has a kind of locality to it. It could have been that we can only find out what the preparation was by doing these sort of joint measurements. We could imagine a world like that. It would have a certain kind of holism to it. It's impossible to figure things out unless you do joint measurements. Well, quantum theory is not like that. We can figure out what the state was just based on local measurements. But real quantum theory would not have this feature. So if you think about real quantum theory, if I come up with a block sphere representation, well, there's now no sigma y component anymore to my density operators, because sigma y is the one poly operator that has complex coefficients in its matrix. So I know that all the density operators for real quantum mechanics can just be written, they just fall in the disk that corresponds to the sigma x, sigma z plane. And now I can do tomography with just a measurement of sigma z and a measurement of sigma x. Well, what about tomography for 2 of these real amplitude qubits? So these are 2-level systems in the real theory. And now if you do parameter counting, you find that, okay, well, we have density operators on this 4-dimensional vector space, but the density operators now are unit trace, positive, real matrices. And it turns out that there's exactly 4 times 4 plus 1 over 2 parameters in such a matrix. I lose 1 for normalization, so I have a 9-parameter family of states I can prepare for these 2 real amplitude qubits. And if I just do these local measurements, identity sigma z or sigma x, on each side, I have 9 possibilities, but one of those, which is the identity cross identity, gives me no information. So I have 8 parameters. And that's not enough. I'm missing 1 parameter. And the reason is, if you ask me why is that, if I look at the matrix sigma y tensor sigma y, there's I components in each of these guys, but when I look at this matrix, those i's squared and they become real. This matrix on the 4-dimensional space is real. So the state of the preparation of 2 real amplitude qubits can have a component of this guy in it. But I can't find out the coefficient of that component using any of these measurements because sigma y tensor sigma y, I mean, I can't measure sigma y locally. That would be complex locally. So this is something I cannot access via local interactions. So to be able to figure out all these parameters, I would have to get those 2 guys together and do some joint measurements on them. So a real theory of quantum mechanics over the real field would have this funny feature that local tomography was not sufficient to figure out the state, and so it would have this kind of holism. So what people have often done is they said, let's assume that we don't have that kind of holism. Then that's one reason to prefer the complex over the real. Yes?
Why do you have to assume that in real quantum mechanics, the spin would be still measured by SU2 elements? Why does it have to be sigma x, sigma z? Why can't it be some elements of group SO3, for example?
You could, so I'm not exactly sure what you're proposing, but let me put it this way, that I've defined a particular way of understanding what one could mean by quantum theory over the real field. That was sort of my first slide. You might come up with other alternatives to quantum theory that would be different from the one I've described here. And those alternatives might also somehow fit the description of being sort of abandoning the complex field. I don't know precisely.
No, I just mean when you consider spin.
Yes.
I mean, you just throw out sigma y because it's complex.
Yeah.
And why can't you find some kind of representation of the spin? I don't know. Like, if you want to talk about spin, why can't you find just a matrix representation of talking about spin that just has real components? Is it?
So you're saying, does there exist like the SO3 Lie algebra on a 2-dimensional Hilbert space using matrices, all of whose components are real? So that question about representation theory, I don't know the answer to offhand. I suspect the answer is no. Yeah. I suspect the answer is no. And I suspect, therefore, that you could argue that there's no way of having a full representation of SO3 on a real 2-dimensional system. But I'd have to look into that. Other questions? Yeah?
Yeah, it might be the same question, but I wasn't completely able to follow, so I'm not sure. I might just ask it. But, so what I'm puzzled about is that you seem to assume that sigma x and sigma z are the relevant operators for, and in this case, even though you're working in a different context, working over real vector space. So is it obvious that you should keep use of those operators?
In fact, I could have chosen any 2 of the polys as my spanning set, and then just used real coefficients. So just taken the linear span of any 2 elements in that space of Hermitian operators. The linear span using the reals, and that would have been fine. I just chose sigma x and sigma z because they're the ones with the real coefficients. But really, I could have done this with sigma x and sigma y if I wanted to. It's really the span of those Hermitian operators that's relevant for describing the theory. Just like we saw earlier, it's the convex set of states that's important, not how I embed that convex set in the embedding space. I could rotate it any way I like. And as long as I rotate the effects as well, all the probabilities stay the same. So you're absolutely right that there's a conventional element in what I told you about that I just used because I thought it would be simplest. Okay, so that's it for operational axioms. Next week we're going to talk about realism again and hidden variables and no-go theorems.